Swayam Prabha. Digital India. Educated India.
So, in this class we will be looking at the word embedding using Word2 Vec. I will be taking you through the concepts applied in the Word2 Vec. This was developed by Google in the early 2013 or 14, and I will be taking you through the code as well as through the techniques and also through the mathematical equations on how word embeddings are created using the neural network using two different concepts. Before we get into that, I am sure you are familiar with the word embedding that we discussed earlier in the latent semantic indexing or latent semantic analysis, where we actually decomposed a matrix into three components. I hope you remember that, right? When you decompose a matrix that consists of term documents, it gives you three different matrices. One is the left singular matrix, other one is the right singular matrix, and then the middle one we call it as the singular matrix, right? And then if you look at the dimensionality of the matrix, which is driven by the singular values in the diagonal elements of the singular value matrix, we would be able to reduce the size of the total matrices by curtailing the size of the singular values. I hope you remember that as well, right? So, in the same fashion, we are going to be looking at a neural network to create a similar concept where we can create word embeddings. In the case of LSI, the left singular matrix, if you are using a term context matrix as the input and then use the SVD to decompose that into left singular, right singular and singular matrix. The left singular would contain the word embeddings, and then the right singular matrix would contain the context embeddings and so on, right. So, if you really see how that happened, to understand whatever I mentioned, I'll draw this in the matrix form. Okay, this is your term, and this is the context, right. When you decompose this, we get three different matrices like this. Okay, and then here this is your singular matrix where you will have lambda 1, lambda 2 and so on. This is your left singular matrix, which is giving you the word embedding. This one is your and this is the context, right, context matrix. So, the matrix sizes are defined by the number of elements in the left in the singular values. So, I can reduce this to a smaller number, so that my size of the left singular value reduces and the context also reduces to match the size of the singular matrix. Okay. So, in that way I can just have the word embedding to be of size, let us say 100 elements or 200 elements or 300 elements, and depending on what is the kind of accuracy you want to have, you can increase the size of the elements in the word embedding. So, we are going to be doing a very similar approach using the neural networks, and this course this session is all about this. Okay. So, in this session I will be talking about what is a continuous bag of words, and then what is a skipgram model, and then what is one word learning, what is the input layer that we are going to be using, and then what is the hidden layer, what is the size, how is it connected to the input layer, and then there is an output layer, and then how the output layer is connected to the hidden layer, and later we will also see how those input hidden weights and the output hidden and the hidden output weights are modified based on the loss function. and then we will see how and what is learnt during the process of the training. Later we will see why this model is extremely difficult to implement with respect to the size, and then how we can reduce the computation complexities using subsampling, negative sampling, and then hierarchical softmax and so on. And finally, we will talk about the limitations of the Word2 Vec. All right. So, let us jump into the Word2 Vec model. See, the goal here is again very similar to what we saw in the LSI. We want to process each word in the vocabulary of words to obtain a respective numeric representation, right. So, instead of just having it as a one hot vector, I want to represent the word in terms of vector, which contains about 100 elements, 200 elements, 300 elements and so on, and let us see how we can get to that level. And then we want to be able to reflect these semantic similarities when we finish training the network. We want to be able to capture this syntactic similarities when we finish the training of the network, or can we capture both in one shot. We will try to map the plurality of each words to the respective vectors, and then try to see how we can merge the vectors so that it is a combination of the respective vectors. That is, we are trying to combine multiple words which are similar and then push them as one vector. Okay. So, that is what we mean by the plurality here. So, now I also will try to refresh your memory in terms of what are context words and so on, and then describe them with respect to the context word, what is a continuous bag of words and what is a skip gram and so on. Okay. So, if you look at the context words, and you remember the conditional probability that we used in terms of identifying or predicting the next word in the language model. So, in the language model, the next word is the last word in the context of words, correct. That means, when a context of word is given, the next one to the context is the word that you want to predict. So, in the case of continuous bag of words, a central word is surrounded by the context words. So, in the case of the language model, let us say so, this is your context word in the case of the language model, right, and this is what the word you want to, this is the word you want to predict, correct. So, now in the case of continuous bag of words, we have an example here at the bottom, wish you many more happy returns of the day. Okay, this is the sentence that I want to be able to process. Here I am taking the window size as 5, 1, 2, 3, 4, 5, and then the central word is the one which I want to identify given the context words of more happy of thee. Okay. So, given those context words, I want to be able to find out what my central word is. Okay. In the case of this skip gram model, given the central word, I want to be able to predict the context words surrounding the central word. So, that is a difference. Okay. So, in the case of the continuous bag of words, given the context of the surrounding words, I want to find the central word. In the case of the skip gram model, given the central word, I want to find the context. So, in this case, we have an input layer, okay, and then we have a neuron that sums all the incoming weights, and then we have an output which predicts the central word. Okay. So, in the case of SIBO, we have, in this case it is a 5 window word. So, we have WT minus 2, WT minus 1, WT plus 1, WT plus 2. Okay. So, every time we will be inputting one of these to the network, and then the linear sum is taken and then the output word. So, based on the understanding of the continuous bag of words, so we will now define a neural network. So, in the neural network you are going to be having a context word coming in as the input, and then it is linearly summed using the input and the weights, and then the output is generated using the weights here and the hidden layer values, and then finally we take a softmax to find out what is the right word for us. So, in this case, since we are going to be using the one hot vector, I will not be able to input all the words together in one shot. So, I will be inputting only one word at a time in this case. For example, if I take wish as my first word, I look at the one hot vector related to the wish, and then that will be input here. Okay. So, as I mentioned earlier, CBOW is used for learning the central word. So, we want to maximize the probability of the word based on the word co-occurrence within a distance of n. So, in this case it is 5. Okay. If the input size is 100, then the output size also would be 100. So, it will be 100 by 1, input also would be 100 by 1. So, they have to match. So, that is when you do the softmax, all the 100 values would be output in the output layer, and then you pick up which one you want to really take as the predicted output, and then you start doing the back propagation, and back and forth you adjust the weights and calculate the summation, predict the output. In the same fashion, we would be training the skip-gram model as well. So, in this case the input is going to be only 1, right. That is the central word. Central word is going to be finding the context surrounding that central word. Okay. So, the process is the same. Again we will be using a one hot vector as the input, and then if our vocabulary size is 100, and there will be 100 elements in this one hot vector, and then we can decide the size of the neurons in the hidden layer, let us say 10. Okay. And then the output would be also of the same size as the input, even though I have given all those things, all those context words. In this case we will be computing the context word one at a time, and then the size of the output would also be 100. There will be 100 neurons in this case. Again in this case we will be applying a softmax, so that the values are distributed across all the 100 elements, and then we try to maximize the probability of obtaining the right word in the output. Okay. Or we will try to formulate an error function and try to minimize the error function and do the back propagation, so that the error is minimized after certain epochs of time. So, in this case, as I mentioned, SG is used to learn the context word given the central word. So, we would try to maximize the probability of word based on the word occurrence within the distance of minus n plus n from the central word. So, now let us see how we can prepare the training data, right. This is the most crucial part in any natural language process application, right. So, when a given sentence is given, so we are given a very cleaned up sentence here. So, there is no need to do a lot of pre-processing with respect to removing removing certain literals or numbers or whichever are not required for the understanding of the word. Okay. In this case we are going to be using a 5 window size, and we will be capturing the training samples using that. So, when we start with that 5 grams, so what happens is there is a start symbol in the beginning, right. So, that is when this becomes a central word. So, there will always be a start symbol and an end symbol like this. Okay. So, we start capturing the words that are surrounding the central word. Okay, so now wish you as 1. So, and then we are capturing the bigrams of each of those in this case. Okay. And then wish many. So, we have you and many as the context word for wish. So, we are ignoring the start symbol for the moment here. So, when you move the window slowly across, right, the central word changes and the corresponding context words also change. So, for this case you is the central word, wish, and you more, you happy, correct. So, again you move the window, so slide the window to the next word. Now, many is your central word and you have many you, many wish, many more, many happy. So, in this way you keep moving the window across the entire corpus and then form the bigrams of all those words and then create a training sample. Okay. So, do not worry about the repetition of certain bigrams in this case. Okay. There will be repetitions when you start processing a large corpus. So, we do not need to really worry about this at this point in time. So, in this case what we are going to do is we know which one is the central word when we take it. So, first one is always the central word, right. So, this is going to be input into the neural network. Let us say if you are looking at the CBOW model. So, I will use wish, I will take the corresponding one hot vector related to this and then use that as the input for the network. So, understand how this is created, right, how this training data is created. Okay. So, again I am just giving the same network model, but in a different style. So, we have this is a bow tie model. This is the input layer of size v. So, xi would be x equal to x1, x2 to xv. That would be the size of the input. Supposing if you have 1,000,000 words as the vocabulary, then the number of elements in the input layer is 1,000,000. Okay. Hidden layer size is smaller than the input layer size. We can go up to the value of 300, or if you want still further finite distinction, you can go up to 500. Okay. So, that means the hidden layer will have 500 elements and we will be connecting 1,000,000 to 300 or 500. So, that many weight that you will see. So, that means this is 1,000,000 into 500. That means you will have 500 million connections going. In the same fashion, since the input layer and the output layer size is going to be the same, both will have the same V dimension. If you are using 1,000,000, this also would be 1,000,000. Again, the number of elements in the matrix W dash here would be 500 by 1,000,000. Okay, so, that is the size of that. Let us not worry about the size at this point in time. Let us only worry about how we can really make this neural net functional. Okay. As I mentioned earlier, there will be only one input we will be providing at a time. So, one word will be input and the weights are initially randomly created, and then the hidden layer is computed by using a dot product of the input layer and the weight vector, and then later the output values are computed by again doing the dot product of the hidden layer elements and the weight vectors on the output layer side. Okay. So, this is the simple representation of the one word learning neural network using the bag of words. Okay. So, as I mentioned earlier, so we are going to be using a one hot vector as the input element, and then you know well that the values in the one hot vector would be equal to 1 only once in the entire vector for a given word. Okay. The rest of the values would be 0. So, it also gives you the index of that word in the vocabulary list. So, this defines how the one hot vector is given.